particular question. Let me just rub this off. Let's start again. So what's going on over here? They told us that that there's 2 moles of dinitrogen tetroxide and it was sealed in a container. So right at the beginning, initially, right at the start, there are, okay, so your initial moles, you got 2 moles of dinitrogen tetroxide. So tetra is 4, di is 2, so it's probably this one. And the moles of NO2 are, he didn't add any moles, so that's exactly 0. So what happens after that? After equilibrium had been established, the total pressure was 140 kilopascals, so that's the total pressure of the container. And the mixture of gases contained 1.84 moles of dinitrogen tetroxide. So over here, at equilibrium, the moles of dinitrogen tetroxide had decreased to 1.84 moles. So that means that you started off at 2 moles, but now you have 1.84 moles. So how many moles are missing? That's 0.16, right? These moles are missing. You started off at 2. Now you have 1.84. So that means 0.16 moles are missing over here. So that indicates that 0.16 moles must have reacted. And they must have reacted to produce what? They would have reacted to produce this thing. So according to the ratio, 1 is going to produce 2. So 0.16 would produce 0.32 moles. That's the quantity that's going to be produced. So over here, you'll have an extra 0.32. This is 0.32. So over here, you'll have an extra 0.32 moles. So your moles at equilibrium are going to be 0.32. So this is what's happening, that he stated that he started off at 2 moles. This is the information that was given. That at the beginning, right at the start, you had 2 moles of N2O4. And when equilibrium was reached, you just had 1.84. That means 0.16 moles went missing. So that indicates that 0.16 moles must have reacted to produce this thing. And it's 1:2, so over here 0.32, double the amount would be produced, which would be 0.32. And that's why you get 0.32 moles at equilibrium. Is this clear to everyone? Emma, did you get this? Is this clear?
Yes.
Achha, so you found your equilibrium moles. This is the position of the container at equilibrium. 0.32 moles of NO2 are present, and you have 1.84 moles of 1.84 moles of this thing in 204. And after that, he's asking you to calculate the mole fraction of each gas. So these are your total moles at equilibrium. So what is the mole fraction of and eventually he's going to ask you about the partial pressures as well. Like if you go over here, he would ask you about the partial pressures of each gas, and then he's going to ask you about the Kp of you're supposed to find the value of Kp. So we're going to directly do all of this. So we're going to directly do all of this over here. So the total pressure of this gas combined is 140 kilopascals, which was stated earlier. So what's the pressure because of this gas alone? I mean, these two gases combined are exerting a pressure of 140 kilopascals. So what's the pressure because of the NO2 gas? It's going to be the percentage of NO2. So it's 0.32 moles out of the total moles, which what are your total moles? You're going to add this moles with this moles. So the total amount of moles of gas at equilibrium, what number do we get? What's 1.84 divided by 0.32? Sorry, 1.84 plus 0.32. That I think is 2.16. So out of the total moles, which are 2.16, the amount of NO2 is just 0.32. So that's the fraction of gas that NO2 occupies, and you multiply it by 140 kilopascals. And similarly, you're going to find the partial pressure because of this gas over here, So the amount of moles of this gas are 1.84 divided by the total moles of gas, which are 2.16, and you multiply it by 140 kilopascals. So what are the two numbers that you're getting for this? Can anyone quickly tell me what the answer is?
119.3 for the 1.84.
119.3, right?
Yeah,
That's a kPa.
kilopascal.
And this one would be the leftover pressure. Like the total pressure was 140 kilopascal. So you can either calculate this or it's going to be what, 20.7?
Yeah, 20.7.
So you're getting 20.7 kilopascal. So you found the pressure. So the pressure is going to be exerted. Like this is the total moles of gas at equilibrium. So the pressure that the total moles of gas are exerting are 140 kilopascal. So the pressure would be what each gas would individually exert would be according to the ratio. So it's going to be mole fraction or percentage into the total pressure. So you get these values, and you have to calculate the value of Kp. I mean that's what he's asking in the next step. So Kp is the pressure of the product, which is N2O4 over here, and it's going to be divided by the pressure due to NO2, and that one is going to be squared. So Kp is what? It's what is N2O4? That's 119.3 kilopascals, and the other one is 20.7, and that's going to be squared. So what answer do we get for this? What's 119.3 divided by
0.278.
0.
278.
So we're getting 0.278, and what is going to be our unit? It's going to be kilopascals divided by kilopascals squared. So I can calculate the unit. It's going to be kPa divided by kPa squared. So the unit is going to be kPa, kilopascals to the power -1. That is what our unit is going to be. Okay, is this clear?
Yes.
So then, one second. Now the next question is, in the next question, what is being asked is, I think no calculations. He's just asking you to write the expression for Kp. Now, the expression. So now the expression for Kp in that case is that it's going to be, just a second. Just hold on 1 second. As just coming back to this, I just have to calculate the value of, just a second, my mic is up here. So coming back to the value of Kp, which is he's just asking for the expression for Kp, and the expression for Kp is going to be products over reactant. So, and you have to find the unit. So it's going to be the pressure of NO. That's going to be power 4, and divide that by the pressure that's because of the other product, which is H2O. So that one is going to be power 6, and the whole thing would be divided by the reactants, which in this case would be pressure of NH3, and that one is going to be power 4, and the pressure that's due to O2, and that would be power 5. And he's asking for the unit, so I think he's using kilopascals over here, right? So keep that as the unit. So it's going to be kilopascals. The top side would be power 10, like it's kilopascals and power 4, and you have power 6. So that would be power 10, and at the bottom it's going to be kPa, and that one is going to be power 9. So what you're going to get is just kPa to the power 1. So that's going to be your unit in this case. Now, part B is what will be the effect on the yield of NO of each of the following in each case explain. So this is about Deshattler principle. He's already told us that the forward reaction is exothermic. So that is coming, that is exothermic, that's given, which means that the reverse reaction is, that one is endo. So what would happen to the yield of NO? Where would the equilibrium shift if you increase temperature? Which reaction is favored? Endothermic or exothermic if you increase temperature?
Endo.
Okay, so that's going to be endothermic, which in the buff scenario is the backward reaction. And if it's the backward reaction, the yield would be considerably lesser. It's going to decrease. Less NO would be produced. There's going to be more backward. There's going to be more backward reaction that would be happening or taking place. And the next part is what would happen if you decrease the applied pressure. So when you decrease pressure, more gas or less gas? Which side is favored? Whenever you decrease pressure. Anyone?
More gas side.
Okay, so it's going to shift to the more gas moles. It's going to shift to the side which has more gas mole side. And in this case, I think it's more gas is in the forward side. I mean, in the forward direction, you have more gas. There are 10 moles of gas, whereas in the backward side, there are just 9 moles of gas. So more gas is forward. Hence, more gas mole side, that's going to be forward, and the yield is going to increase. There's going to be more forward reaction, yield increases. I said, let's move on. Focus on another KP question. I'm going to talk about. Let's try and solve the whole question. Like the first part is also interesting, but that's obviously about the Deshattler principle. Now over here is saying that the conversion of sulfur dioxide to sulfur trioxide is carried out at a temperature of 400 degrees centigrade. So it's SO2 reacting with O2 and in equilibrium with 2SO3. That's the contact process, and the forward reaction is exothermic in this case. Now the question is, you have to use the Deshattler principle and the reaction kinetics to explain one advantage and one disadvantage of using a higher temperature. He's using a temperature of 400 degrees centigrade, which is kind of a higher temperature. So first thing, what are the two things that could happen at higher temperature? The first thing is he wants a comment on both things. Not just the Deshattler principle, but also on the reaction kinetics. So we're going to focus on the Deshattler principle. We just studied that higher temperature favors the endothermic reaction. Which is which reaction in this case, backward or forward? Which one is the endothermic reaction?
Forward.
The enthalpy change. The enthalpy change is given. It's given. It's negative. If it's negative, that indicates that the forward reaction is the one that's exothermic. Okay, so the forward is exo. The backward is the one which is then going to be the endothermic. So endothermic reaction is favored, which in this case is the backward reaction. So that's not a good thing. That means the yield decreases. Okay, so you're going to have lesser yield. So that's one disadvantage. But what's the advantage of using a higher temperature? If you use a higher temperature, what happens to reaction kinetics? Reaction kinetics it's the rate of reaction. Do you have a faster reaction or a slower reaction at higher temperatures?
Faster.
Okay, so you have, I mean, and you've given a lot of lines and it's a 4-mark question. So you're not just going to write faster, but also give some explanation that there's going to be more kinetic energy. So there's going to be particles travel faster, so there would be more frequent and effective collisions. So they would collide with each other more frequently, plus more violently as well, because they have more energy. The particles are more energetic. Anyways, so that's a good thing that you're getting a faster reaction. So the thing is that at a higher temperature, there's less SO3 being formed, but at least the advantage is that it's forming very quickly. So even if you get a small amount of SO3, but you get it very, very quickly, so that's kind of a trade-off. Uh, it might be better than getting more SO3, but getting it after a very long time. So the advantage of using a higher temperature is that the whole thing happens very quickly. So you don't have to wait a lot. As anyways, they're asking for the KP for this specific expression. So this one. So it's going to be just the expression, I think. So it's pressure of SO3, that's going to be squared. And the whole thing would be divided by the pressure that's due to SO2. That would be squared as well. And the pressure, the other reactant is O2. That's just going to have power 1. So we've written down the expression. Now it's all about calculating KP. So starting with the equation, so we obviously have to write the equation again and do the whole initial moles and final moles thing. All questions are kind of identical. What are your initial moles? What did you add initially in the container? It's given over here that he added 2 moles of sulfur dioxide and 2 moles of oxygen. So these, so these were added, right? 2 moles of SO2 and 2 moles of O2, they were added into the container. And they were put in a flask and left to reach equilibrium. So there was absolutely no SO3 added. Like the first statement, nothing was added, no SO3 was added. And then obviously a reaction started, forward reaction happened, backward reaction happened, whatever happened at equilibrium. The pressure in the flask was 2 into 10 power 5 pascals, and the mixture contained 1.8 moles of sulfur. It contained 1.8 moles of sulfur trioxide. So at equilibrium, there's 1.8 moles of sulfur trioxide. So those are your equilibrium moles. You've gotten 1.8 moles. You started off with 0 moles. Now you've got 1.8 moles. So that indicates that an extra 1.8 got produced. Right? There's an extra 1.8 getting produced. So there must have been a forward reaction. 1.8 moles are getting produced, a reaction took place, and 1.8 moles are getting produced. Now, based on this, if 1.8 moles are getting produced, according to the ratio, how many moles of SO2 must react? It's the same ratio. 2 SO3 are produced by 2 SO2s. So 1.8 are going to be produced when 1.8 SO2s react. So over here, you'll have 1.80 moles. That would be taking part in the reaction. That would be reacting. And what would be the ratio? How much O2 would react? 2:1, so 1.8 getting produced. So over here, it's going to be 0.9 moles that would react. Is this clear to everyone? Yes or no? Is this clear?
Yes.
Yes.
So anyways, your starting moles were 2 moles, 1.8 moles have reacted. So subtract those, they're gone. So what are you left with? You're left with just 0.20 moles. Similarly, you started off with 2 moles of O2, now 0.9 are gone. 0.9 have taken part in the reaction, so you subtract those 0.9 moles and you're left with 1.1 moles of this. So finally, you have your equilibrium moles. Everything at equilibrium is known. You have these many moles of this, and this. Three things are present in the container, and together, all the three things are exerting a pressure of how much? They're exerting a pressure of 2 times 10 power 5 pascals. So, uh, so all of them together are exerting a pressure of 2 times 10 power 5 pascals. So I'm going to find the individual pressures uh, for each one of them. So I'm going to find the pressure because of SO2, the partial pressure because of SO2. So it's going to be mole fraction of SO2. It's going to be, what are the total number of moles? That's 3.1, right? 1.8 plus 0.2, that's 2, and then 1.1, that's 3.1. So out of the total moles, the amount of SO2 is 0.2. That's the fraction of SO2 in the container. You multiply it by the total pressure, which is 2 times 10 power 5. Similarly, you calculate the pressure because of O2. The O2 moles are 1.1, the total moles are 3.1. So out of 3.1 moles, the amount of oxygen is 1.1, and you multiply it by the total pressure. And the last one is the pressure that's because of SO3. So again, make sure that you can have a look. It's a 5-mark question. So it's a big question. It requires a lot of working and steps. So the pressure because of SO3, that's going to be, SO3 has 1.8 moles. So out of the 3.1 moles, 1.8 are, and you multiply it by 2 times 10 power 5. Can anyone tell me what the values are for each one of them?
One two nine zero three for the first one,
It's 12903.
and 70967 for the second.
How much?
70,967.
960?
7.
It's 96.
967.
Okay, it's 967. And what about the last one?
116129.
So the last one is 116. 116? 129?
Yes.
So that's your last one, right? So you found your partial pressures. The only thing is you have to place these values in the Kp expression, which we had calculated earlier. So you have to place these values in this expression over here. SO3 squared divided by SO2 squared into O2. So we're going to just do that. SO3 squared, that's 116. Be very careful with your calculator. It's going to be squared. Divide by SO2 squared, that's 12903 into the pressure that's because of O2, that's 70,967. So what's the final value of Kp, which they're looking for? Mahad, do you have a calculator? Ahmed? Anna?
So one second.
1.14 into 10 to the power negative 3
So we're 1.14
into 10 to the power negative 3.
negative 3. And what's the unit? It's going to be pascals to the power -1. Like you can go and have find the unit over here. It's going to be Pascal squared divided by Pascal squared into pascals. So it's going to be pascals to the power -1. That's what your unit is going to be over here. So we're done with this question. Let's do the next one. The all questions are same. I mean, this one is kind of exactly the same, except now he's talking about the Haber process. So we can do everything again. And if I do this, it's N2 and H2 in equilibrium with NH3. So this is N2 plus 3H2 in equilibrium with two NH3s. As anyway, so we're going to find the initial moles. I mean, we already have the initial moles. So the initial moles that we have are that he added 2 moles of nitrogen and 3 moles of H2. Those are your initial moles. 2 moles of this and 3 moles of this thing over here. And they were just put in a vessel and left to reach equilibrium. So there is initially no NH3. And then you had your reaction, and eventually it's going to reach equilibrium. So forward and backward reactions are taking place. Eventually equilibrium is reached. At equilibrium, the total pressure is 2 times 10 power 7, and the mixture contained 1.6 moles of ammonia. So at equilibrium, you have 1.60 moles of ammonia. So the rest of the part is do everything exactly the same. There were no moles of ammonia at the start, and now you have 1.6 moles. So that means 1.6 moles got produced. They got produced in the reaction. There was some forward reaction. Now use ratios. 1.6 getting produced. It's 2:1. So where how much N2 would react? Half of that. So that means 0.8 must have reacted. And it's 2:3. So how much, according to this ratio, how much H2 must have reacted? Like 1.6. How much of H2 would react according to 2:3? What's this value?
2.4.
Okay, that's going to be 2.4. That's going to be taking part in the reaction. 3 produces 2, so 2.4 would produce 1.6. So these are the moles that are taking part in the reaction. So 0.8 is gone, they've reacted, and 2.4 are also gone because they've reacted. So what are you left with? Started off with 2 moles, and 0.8 out of them are gone. So this is 1.2, right? And for the other one, you started off with 3 moles, now 2.4 are gone, so you're left with 0.6, right? TK, is this clear?
Yes.
And then obviously, because it's a KP question, is asking you to calculate KP. So you have to find, I mean, you found the equilibrium moles of each one of the reactants. The total moles of gas are, what's 1.6? What's 1.6 plus 0.6? That's 1.8. 1.8, I think it's 3. Can anyone double check? So total moles of gas combined are exerting a pressure of 2 times 10 power 7 pascals. So what are each one of the individual gases exerting? This one would be 1.2 divided by 3 times...
Sir, the total is 3.4 moles, not 3 moles.
Yes, it is 3.4. Just a second. So this one is 3.4 moles. So out of 3.4, 1.2 is N2 gas. So its pressure would be proportional to that. So it's going to be fraction, but it's percentage multiplied by the total pressure, which is 2 times 10 power 7. For the other one, it's 0.6 divided by 3.4 times 2 times 10 power 7. And the last one is 1.60 divided by 3.4 times 2 times 10 power 7, right? Hopefully everything is fine. Achha, now, because he wasn't really interested in the working, he just wants the value of KP. Make sure to do one thing, that no need to solve them right now because a lot of things get cancelled out. So you'll just be using your calculator a lot. Put these values in the expression of KP, which is going to be NH3 concentration squared. So this would be squared. So it's going to be 1.6 divided by 3.4 into 2 times 10 power 7, right? 2 times 10 power 7. That's the product. That's going to be squared. So it's going to be NH3 squared divided by N2 and H2 cubed. So N2 is, what is N2? It's 1.2 divided by 3.4 into 2 times 10 power 7. And that's power 1. And the other one is H2 cubed. So that's 0.6 divided by 3.4 into 2 times 10 power 7. And that would be cubed. As anyways, it doesn't really matter. You just have to solve them. I mean, I thought things would be easy to cancel out. They're not easy to cancel out. So it's better to just solve them. Solve this, solve this, solve this, then divide everything, and you'll find KP. You can try and do this question. I say, and is this clear?
Yes.
Okay, so just remember, all questions are kind of almost the same. Try and solve this question now. Do it on your own. This one is, I mean, this is the reaction. It's, I think, the previous part is missing, so I'm just going to take this one, H2 plus Cl2, that's in equilibrium with 2 HCl. So let's assume this is the reaction that's going on. In this question, he gave you, he's talking about HCl decomposing, so I think it's the other way around. So I think HCl is in the reactant side, which decomposes to form, H2 and Cl2. So there's 0.3 moles initially. So that's your initial moles that are given. That's those are 0.3 moles. Right at the beginning, 0.3 moles. And the resulting equilibrium mixture was found to contain, so once equilibrium had been reached, there was no H2, there was no Cl2, but at equilibrium, he's saying he had 1.5 times 10 power minus 2 moles of Cl2. So that is, what is 1.5? That's, I think, 0.015 moles of Cl2. So calculate, I mean, the whole question is about Kp. He must have given the total pressure. Just, I mean, somewhere there must be. I said, sorry. Now in this case, there's no pressure given. Okay, try and solve this. The total pressure is not given. So take the total pressure as P, because we don't know what the total pressure is. And try solving the question just using P. I mean, do everything the same. Find the moles at equilibrium, then find the mole fraction multiplied by the total pressure. Write the Kp expression, put in the values of Kp in that expression, and try and find out what the value of Kp is. Can everyone try and do this right now? I mean, just calculate Kp for this question and use P as the pressure. The total pressure of the container is P. So this one, everyone send this question. You've got 10 minutes to solve this question. Try and solve this question and send it to me. Okay? I'll be waiting for the answer on WhatsApp. Try and solve this question. Is this clear? Any questions about this question? I mean, it's exactly the same. Just take total pressure as P. That's it. So everyone try and solve this and send me the answer. I'm disconnecting from Zoom, waiting for the answers on WhatsApp. Say, okay, everyone.
Lapis.
Take care, Hafiz.
elapsed.